Okay, in our previous video, we learnt how to find the derivatives of functions using our first principles. Now that method works, but it's also awfully tedious. Okay, and thankfully, we've got a lot of rules that we can use so we can avoid that process wherever possible. Okay, so some of our rules, okay, our first one that we're going to look at is if f of x, our function, equals x to the power of n, we're saying n is a positive integer. Okay, so it's just a positive whole number. Okay, then f dash of x, remember our derivative, is equal to n times x to the power of n minus 1. So what's that mean? Okay, if I had f of x equals x cubed, okay, then my derivative, okay, so we take that power that we had and bring it down the front, okay, then we times it by x to the power of 1 less than my original power. Okay, so we bring our original power down, reduce the power by 1. Okay, if f of x equaled x to the 6, okay, then f dash of x is going to equal, bring the 6 down the front, okay, and then times it by x to the power of 1 less than 6, which is 5. Okay, so we're always just bringing our original power down, reducing our power by 1. Okay, so there's a few different things that we can look at with this and a few special cases. Okay, so if we're looking at derivatives of polynomials, if f of x equals c, okay, so c is just a constant, so this could be like f of x equals just 2. Okay, then f dash of x is going to equal 0. And this makes sense because if you think of a graph of just f of x equals c, it's just a constant, so it's just a straight line, straight horizontal line. Okay, well we know our gradient of that line is 0 everywhere, so that makes sense. Okay. We're looking at a linear function. If f of x equals mx plus c, then f dash of x equals m. Again, that makes sense, okay, because we know if we've got an equation like this, okay, then the gradient is constant all the time, and we know from our previous work it's always equal to this m value. So this is all reaffirming things that we already know. Okay. If we have f of x is equal to k times some other function g of x, then f dash of x equals k times g dash of x. Okay, so our example there would be we had f of x equals 3x squared. So we've got this constant k at the front. Okay, then what we do is we say f dash of x is going to be 3 times 2x, because the derivative of x squared is going to be 2x, which gives us 6x. Okay. So we're just taking that power that we had, bring it down the front, and if there's a constant there, we're just multiplying them together. Okay. If we've got two parts, okay, so we've got f of x equals g of x plus h of x, then our derivative is simply going to be f dash of x equals g dash of x plus h dash of x. So for example, okay, if f of x equals x squared plus x cubed, okay, we do each of these parts separately. Well, we say x squared becomes 2x by bringing that power down and reducing by 1, and x cubed becomes 3x squared by bringing that power down and reducing the power by 1. Okay, and this works exactly the same whether it's adding or subtracting. So if we're subtracting, the same thing happens. So if we had f of x equals x cubed take x squared, okay, then we're simply going to have 3x squared minus 2x by reducing that, bring that power down and reducing it by 1. Bring the power down, reducing by 1. Okay, so I've got a few examples we can look at. Right. Our first part is actually, well, hang on, we keep using this f of x. Okay, but a lot of our functions are written as y equals something. Okay, in this case, y equals 3x squared. Well, what do we do then? Okay, well, this is a different type of notation. Okay, and where we were saying we had f dash of x before, we can also use what we call Leibniz notation, which is simply that our derivative equals dy on dx. Okay, so we say dy dx, okay, is our derivative. Okay, so instead of, so we've got, if our function is f of x equals something, then our derivative is f dash of x. Okay, if we've got y equals something, then our derivative is dy dx. Okay, otherwise the process goes exactly like it would. Okay, so we've got a couple of examples here. Okay, so if f of x equals 2x cubed, find f dash of x. Well, remember, we've got the 2 here, that's fine. We go 2 times, we'll bring our power down, 3 times x, reduce our power by 1, squared. So it's going to give us 6x squared. Okay. If we're looking at something like this, y equals 2x cubed, take 3x squared, take 4x, take 5. Okay, and we want to find dy dx. Okay, what we say dy dx, we just keep doing it in parts, work our way through. Bring our 3 down, times it by the 2, gives us 6. Reduce our power by 1, makes it 2. Okay, bring our power down, times it by our coefficient, so negative 3 times 2 gives us negative 6x. Bring the power down, reduce the power by 1, makes it just x, minus 4x, that's just going to become minus 4, and our 5 going to disappear. Okay, so anytime we don't have an x in there, any term, okay, we treat it like it was a constant, just a little separate function by itself, and we know that it's going to disappear. Okay. Okay. A slightly alternative form of Leibniz notation is simply stating what we're looking for. So we don't have to say, if our equation is this, find what our derivative is. We can actually state it like this. We say, we have a d, okay, and then we have our actual function, and then it's on dx. So this is asking for the derivative of this with respect to x. Okay, so it's the derivative of all this with respect to x. Okay, so how do we do it? Okay, well, what we need to do is we need to expand this out. Okay, we need to expand this out. So we'd say I've got 2x plus 1 times 2x plus 1 times x take 3. Okay, so we need to keep working on expanding this out. So we're going to have 4x squared plus 4x plus 1 times x take 3. Okay, we keep expanding this out now. Now 4x cubed, take 12x squared, okay, plus 4x squared, take 12x, plus x, take 3. Okay, collect our like terms. Got 4x cubed, okay, take 8x squared, take 11x, take 3. Okay, now we haven't at this stage actually found a derivative yet. Okay, hence why we've still got this ddx sign in front. Okay, now we can actually find our derivative. Okay, so remember 3 times 4 is 12, x to the power of 2. Reduce that power by 1. Okay, negative 8 times 2 gives us negative 16, x, because we reduce that power by 1. Take 11, because our x is going to drop out, and the 3 disappears. So that is what our derivative would be. So you see the vast majority of work here was simply getting ready for our equation. Getting ready to find our derivative. Okay, our last example here is find the point where the function f of x equals 3x squared take 8 has a gradient of 4. Okay, so what we need to do here is we need to find our derivative first. So we say, well, f dash of x, okay, is equal to 3x squared take 8. Okay, that was our original function, so 2 times 3 is 6. Okay, the power gets reduced, so it's 6x. The 8 disappears. Okay, and we want to know when, so this is our derivative function, or if you like, our gradient function. So it's asking us to find the point where the gradient is 4, okay, where we let f of x equal 4. They say 4 equals 6x, so x equals 4 on 6, which is 2/3. Okay, but what we need to do is we actually need to find the y value as well, because we haven't got, we've only got the x value. We need the point, so we need the y value as well. So what we do is we take this x value and we sub it into the original function, not the gradient function. Okay, that's just going to give us this value of 4 again. We already know that. Okay, we need to put it back into our original function. So we're looking for f of 2/3. It's going to equal 3 times 2 on 3 squared minus 8, which equals 3 times 4 on 9 minus 8. Okay, so 4 on 3 minus 8. It's going to be negative 6 and 2/3. Okay, So the point is going to be 2/3, -6 and 2/3. Okay, so this is going to be the point where this function has a gradient of 4. Okay, so a little bit different type of question for that one. Okay, but hopefully that's enough to get you to your questions on this section.